compañero nuestro, desde hace tiempo, después de haber tenido pues hace una presentación para el recuerdo, luego hizo la tesis doctoral en la Universidad de King's en Belfast y posteriormente pues tuvo hasta los tantos días que me acuerdo, pero creo que esa experiencia doctoral también aquí en y actualmente es el director del Instituto de Astrofísica de Andalucía. Entonces él nos va a hablar de un instrumento para GTC. Entonces me gustaría hacer una historia breve de este instrumento, dado que bueno, que ya ha participado en este instrumento, pues llegó a GTC, un estudio de viabilidad a finales del año pasado, y este estudio de viabilidad pues fue realizado por diferentes comités, de expertos, y también por el SAC, pues el servicio de GTC, y al final se concluyó que era un instrumento demasiado complicado, con un caso científico
Bueno, de todas formas todos me habéis oído, o sea, no tengo que repetirlo, ¿no? Un caso científico también demasiado complejo porque, bueno, decir que pues era un instrumento que abarcaba un rango espectral muy amplio, de 0,3 a 1,7 creo micras, diferentes resoluciones, resolución 4000, resolución 10 o 20.000, no me acuerdo, Ifu, super Ifus, y bueno, realmente era demasiado complicado. El presupuesto creo que rondaba los 40 millones de euros o algo así. Entonces, bueno, GTC decidió pues no aprobar el proyecto. Entonces, Paco Prada, como investigador principal, pues ha decidido, obviamente, romper el consorcio, ya no tiene sentido, ¿no? Y centrarse en las recomendaciones. Aquí hay que decir que el IAC participaba pues más o menos a un 25%, y teníamos un co-investigador del IAC que era Jorge Casares, y entonces pues Paco ha decidido replantear el instrumento centrándose en las recomendaciones de este comité de expertos. Este comité de expertos, la recomendación que hizo fue que el modo más competitivo era el modo de espectroscopía multiobjeto de baja resolución, y bueno, pues ahora va a rehacer este consorcio. Entonces es importante evaluar pues el interés que tiene el IAC en participar en este nuevo instrumento. Ya hay muchos investigadores que me han expresado su interés, y también otra cosa bastante importante, necesitamos tener otro co-investigador, dado que Jorge Casares ya me ha expresado su interés en no seguir, dado que pues realmente su interés científico no está aquí, su interés científico está más en la resolución intermedia o 10.000, 20.000, no se quiera llamar, ¿no? Entonces es importante oír después vuestros comentarios y del interés que tenemos, si queremos seguir participando, y como digo, también es fundamental tener un co-investigador principal. Además, también este comité hizo la recomendación de que este instrumento lleve asociado un número de noches garantizadas, más allá de los acuerdos estos de GTC, que garantiza unas mínimas número de noches. Y bueno, en el comité de seguimiento de GTC se aprobó que se va a hacer una llamada próximamente. Estamos a la espera que José Miguel haga dicha llamada para presentar estos proyectos que se llaman claves o key programs en inglés. Entonces la idea es que este instrumento lleve asociada ya una petición de un número de noches para pues completar unos surveys que se definan, ¿no? Porque no tiene sentido pues hacer un instrumento de survey que luego tenga que ir a través del CAD, que el CAD le dé o no le dé tiempo. Bueno, pues eso es todo.
Bueno, pues sí. Los agradecimientos los hago en español y quiero agradecer al IAC de nuevo por su hospitalidad y es un placer volver. Desgraciadamente siempre vuelvo con muy poco tiempo ahora, pero espero pronto poder pasar al menos una semana o un poco más. Y al coordinador de investigación por organizar la charla y por la introducción que ha hecho. So we'll start the presentation by making a summary of the original proposal. You will see this label in the top of the slides, which is Feasibility Study 2005-2008, which is the instrument that we were proposing to GTC, and the instrument that we have been working for the last almost 3 years, which is Ifu Deployable Experiment. Originally, as presented in the feasibility study, it's a common user intermediate resolution fiber-fed spectrograph dedicated to wide-field multi-object spectroscopy and 3D spectroscopy in the visible and near infrared. It's basically an instrument, or it was an instrument, that satisfied a lot of science cases, a lot of observing modes, and finally you end up with something which is complex and expensive. So the original site parameters were given here in this table. So a wide field of view, the maximum field of view that you can accommodate at the NASMED platform, 3 different observing modes, multi-object, Super IFU, which is a big fiber bundle with a big field of view, 30 seconds by 30 seconds, mini IFUs, everything. And resolution were going from 1500 to 30,000. And the spectral window was from the very blue to the near infrared at the end of the H band. So the science cases were covering everything from solar system to cosmology, because we thought about an instrument that will be proposed as common user facility. This was the original consortium. We created a science team with 56 scientists, different working groups, and I really appreciate very much the effort of all people. They did an excellent job. They created about 120 pages of science cases. The people in red were the coordinators, and I think we have to really thank all of them, as well as the instrument definition team. So let me start in more detail about the history of the project. We started the initiative in November 2005. We had at least 4 presentations to the Scientific Advisory Committee of GTC. We basically end the feasibility study December 27. We had a review by GTC office on April 2008, last spring. We got a response in July, and the consortium ended last August. So we have spent €1 million in this feasibility study. So that's something really substantial. It's not only cash, which we have spent in travel and few other things, but we have spent money on consultant and a lot of money in manpower. So this is a number of staff per year, and companies, so we end up with 1 million euros. So from this 1 million euros, we got a small amount from the Ministry of Science and Education, tiny amount from GTC, and the rest, 80%, was coming from the different institutions helping in the project, and not only the IIA in Granada, but also the IAC and other institutions. So this has been already a very important effort, and some of the institutions has put a lot of manpower and time on the project. So the SAC review, I can pass you a copy of the presentation. I don't want to go into all detail. So SAC review recommended to the scope side to produce which they considered the priority for the DTC community, which is an instrument devoted for intermediate spectral resolution in the visible, resolution in the range from 10,000 to 20,000. However, the external review panel, as Arturo said, in their executive summary, they recommended to go into the opposite direction, to go into multi-object spectroscopy survey instrument, basically focusing on multi-object spectroscopy in the optical and near-infrared. So they have different views on the directions to go, but both agree that the instrument as presented was not possible to be built. Now, the new site, what we call site beyond 2008, I just invented this name now. So, it's basically the multi-object spectroscopy mode of site. And then, if you remember the previous table, I have deleted here the modes or features of the instrument that will not be anymore a priority for our consortium. Not only a priority, it will not be really implemented at all. So the location, preferentially we like the Nasmith, but this is question mark because it's up to GTC to tell us where we can place potentially an instrument like this. And this is very important aspect. We really need an answer about that. And we will ask them also now on the light of the new consortium. On the field of view, if we go to Nasmith, we can have this 20 Armenia diameter for the multi-object spectroscopy mode. We will not have any mini IFU at all because our robot positioner will not allow to move these little bands around the field. But for free, because we have the spectrographs, for free, in the middle of the focal plane, in the center of the focal plane, we can have a super IFU, integral field unit bundle, which a field of view of 30 arc seconds by 30 arc seconds, which is really unique. So, number of objects that you can observe is again 1,000, and the SIFU will have many fibers. The resolution and spectral coverage will be from 1500, so that you have full spectral coverage from the optical to the near infrared, and resolution up to 5,000, which is enough to resolve OH skylines and go deep enough to really go to very faint targets, very faint objects. And the spectral window will go, that's a mistake, it's not 350 nanometers, will be 400 nanometers to 1400 nanometers. So we don't want to go up to 1.7 microns because we will be forced to cool the whole spectrograph. And that's something that we don't want to take the risk. We are aware that there is very important science up to 1.7 microns, but cooling, it will not be cryogenic cooling, but still it's an effort because you have to cool everything from the slit and all the whole spectrograph. This is not a limitation. Going to 1.4 micron will be really amazing. We can do a lot of science, especially because we are going to have a very unique feature, which is simultaneous optical and near-infrared spectroscopy. So in one single exposure, you can have both. So this is in summary the instrument. So it will have this multi-object mode. It's the major instrument, and this is Ifu. So you have the light coming from the telescope to the dustbin. You have a wide field corrector to correct all distortions, field distortions, and other aberrations. And then you have a robot positioner, which is a concept developed in Granada together with a company in the Basque, what's the problem, region or country? In the Basque, in North Spain, area, in the Basque area, which is done together with the Berkeley lab, Lawrence Berkeley lab. We basically started from that concept and end up in a similar concept. We will have about 900 multi-object spectroscopy units. So it means that in this 20-minute field of view, which is basically 1 meter diameter, you will have 900 cylinders, and each cylinder will basically be able to get one target, one object, within a small field of view of 45 arcseconds. You will see that later. So the fiber cable depends where the spectrographs are located. It will be 15 meters, 20 meters, 40 meters. It depends. We'll go to 10 identical spectrographs. Each spectrograph can accommodate 86 objects or units. So each unit, multi-object unit, is a bundle of 7 fibers with micro lenses with a field of view of 1.5 arcseconds. And each spectrograph is called dual. All are identical, they are just clones. And in the range of 4,000 angstrom to 1.4 micron, with a dichroic at 9,500 angstrom. If you have resolution 1500, in a single exposure, you will be able to coverage from 5,000 angstroms to 1.4 microns. So in a single exposure, you will have the whole spectral window, optical and near-infrared, up to 1.4 microns. If you go to resolution 4,000, then you need about 2-3 exposures to cover everything, maybe 3. And the spectrographs are very small, very compact, 100 millimeters beam size, so that they are not very expensive. They are simple spectrographs. There is no any technology challenge in the construction of the spectrographs. We have followed the philosophy of the Sloan spectrographs, but we need to build them. That's the challenge, because we never have done it. In terms of science, I will go fast. The reason? The 4,000 limit? Why the 4,000? I will comment that, yes. Yes, I will skip the technical part now and talk a bit about science and then go to technical part. So maybe I'm going too fast, but I want to give you an overview and maybe discussions later. I know there is another talk after, but I will be here the whole day. So, in terms of science, which is the most important part, where is the niche? Why I believe, and a lot of people believe, that this project is unique, and why we believe that GTC will also be unique by having this facility. There is a very nice opportunity here for next decade that GTC will lead survey spectroscopy. And the reason for that is that there are a lot of efforts around the world on deep imaging surveys. So everyone is doing imaging surveys. Everyone is spending millions and millions of euros building wide-field cameras, doing large-scale surveys, and not only in the optical, also near-infrared, and many of them have the goal to get photometric redshifts for different purposes. Dark energy, galaxy evolution, everything. Every one of you knows Cosmos, UKIT, VISTA, Punk Stars, LSST, Dark Energy Survey, Hyper Supercam at Subaru, LSST, and here there are a number of science cases which cover basically everything from solar system to cosmology. But we should not forget also the James Webb telescope, which also does imaging and spectroscopy. So the most important fact is that nobody else except a project at Subaru called WFMOS, which at the moment is pending. So they want to build something similar outside at the prime focus of Subaru. So nobody else is putting effort on survey spectroscopy in 10-meter class telescopes. The reason for that maybe is that there were a general sense in the community in those imaging surveys that there's no need anymore for spectroscopy. Many people thought, well, with all these photometric redshifts, we can do everything that we need. We can do all these baryon acoustic oscillations, no problem. We can do also galaxy evolution. We can do environment, no problem. So everyone said, well, maybe spectroscopy is useful, but not critical for our project. Now, this idea has changed dramatically. And those people are getting really nervous by the fact that they need calibrations, they need redshifts, real redshifts, to understand and correct many of the systematic and biases that they have in the project. And also they recognize that there are things that never can be done with imaging alone. You cannot understand environment, galaxy environment, only with photometric redshifts. That's something that is very, very hard. Except that you have many, many filters, like, for example, Alhambra survey, which is 23 filters, then you may be okay, you can do some studies, but then you can only focus on a very, very small area on the sky. But if you go to standard 4, 5, 6 filters, which are all those major surveys, forget about. So the idea is to focus side in extragalactic and cosmology research, which is not incompatible with other areas of research. I'm 100% sure that you can do a lot of stellar physics studies with this instrument. But if we think about key projects, I have in my mind, and other people in our group also think that few key projects along these lines will really make a big difference. So there are different aspects. I will not go into the details. Dark energy, how we can help to contribute in dark energy, large scale structure, and other cosmology-related projects. The build-up of the stellar mass up to redshift 1 and 10, photo C training. So all these imaging surveys, dark energy surveys, really need spectroscopic redshifts, but not only 1,000 or 2,000. They need 100,000. So they need so many redshifts that only to do that you need to build up this instrument. They are even considering that because they are recognizing that this is needed. And also you can do a lot of issues related to cosmic chemistry and also evolution, galaxy evolution. So I will not go into these details. I have prepared some slides with some science projects that I will skip, I think, but you can get my talk and discuss that later if you wish, because there's nothing really decided or done in terms of the future. So the idea is to meet, if possible, in November, those people who we believe are interested to help in the project and discuss the science key projects to be prepared for the future call of proposals by GTC. So we really want to do a consortium which has the main aim to build up a survey that really need an instrument like this. So we thought about different examples. So take this only as examples. So we thought that something unique will be legacy survey. We call it side 1, which is basically a slow and digital sky survey, but a redshift 1. That's something really fundamental, which is needed, and current Z1 surveys are not really complete because they don't have this near-infrared extension. So they are missing all red galaxies. So if you go to the deep survey, which is really fantastic survey, 50,000 galaxies, 80 nights of Keck. They built Deimos for that. It's really amazing effort. They are missing almost 50% of red galaxies, of galaxies at the end, because their spectra ends at 9,000 angstroms. So that will be really unique, and I know that there are a lot of people in the Sloan community which are very happy about this idea, if possible, at GTC. Yeah, for example, this survey, it depends the depth that you want to reach. But if you want to go, for example, let me put an example. This deep survey, which was 50,000 galaxies up to 24 magnitudes, was 75 nights of Keck. With this instrument will be 25 nights of GTC. If you want to do that survey, no, our field of view is larger than Deimos. No, yeah, sure, no, but I'm not comparing with Sloan. What I'm saying is do Sloan at redshift 1. Sloan is only redshift 0.2, 0.1. No, well, yeah, sure. On area, but on volume will be comparable. On volume will be probably comparable. If you go to 10 square degrees, for example, on the sky, then you are a redshift 1. If you work out the cosmology, you end up maybe with a small volume, but sort of comparable volume. What matters is the volume that you are sampling. Okay? But I would say about 50 nights, 75 nights, depends the area that you want to cover and the depth that you want to go. So all this is survey feasibility studies, what we want to start now doing in detail. So we want to really know. We have done all these calculations. If you're interested in our document, you have all these calculations done for different examples. And you have surveys that could take 50 nights, other surveys that would take 150 nights. It depends on the different parameters that you have. So you have area, redshift range, and magnitude depth. And depending on that, you end up with a number of nights. So the deep complete, that's exactly the example that I thought it was nice to put, is, for example, 50,000 galaxies down to 25 magnitudes complete. Okay, this will be basically about 30 nights of GTC in this case. Okay, and another example is what we call the 1 gigayear slides cube, which is a very high redshift survey, redshift 6 survey, where you have, this is a slide, I will show only this one. This is a simulation, cosmological simulation, done by Gustavo Yepes in Madrid, which includes hydro and star formation and all ingredients of star formation. So this field of view is the field of view of sight. This is 20 R minute, I think. And this is a zoom in on a cluster and objects. So there is no any facility that will be able to do hundreds and thousands of Lyman alpha meters at redshift 6. So only Subaru prime focus camera will be able to detect the objects doing narrowband imaging. So they have this hyper super cam, which will be 1 degree on the sky, to do imaging and to be able to detect the Lyman alpha meter candidates. So because they have these narrowband filters. In fact, with Osiris tunable filter, you can try also this project, but the field of view of Osiris is much smaller. Yes. No, I think I really encourage you to try. So you will be able to detect this Lyman alpha. Of course, the density is small of those objects, so the number of targets in this field of view will be small. So, but there's no any object, spectrographs that will be able in such a field of view to do a spectroscopic follow-up of those objects and end up with samples of 10,000 Lyman alpha meters at redshift 6. That will be really revolutionary because you will be able to understand large-scale structure at a very high redshift when the universe was very young, and also to understand the star formation density of the universe at redshift 6, which now there are a lot of uncertainties. So that's an example, typical example of key project that will be really unique. Nobody else can really do it in a massive scale, let's put it in that way. With the current instrumentation, I fully agree you can start doing this, but breakthrough will come only with this generation of instrumentation. I will skip all those science cases. There is a document which didn't finish at the slide, reassert. I didn't have time. And I will go briefly to the technical details, very briefly. There is a wide field corrector which we have a design. It's a 1 meter, 90 centimeter at Nasmith. It's doable. VLT has one at Flames, so we believe it's possible. But again, we need to know if an instrument like this will be able to go to Nasmith or not. So we really need this input from GTC. So this is the focal plane, how it looks like. This is 1 meter diameter plate, aluminum plate, and you drill holes, 1,000 holes, 860 holes. The different colors are, we were thinking about different units, so that for repair and other things, we'll be able to we can remove it. And each hexagon here is a cylinder, which is shown in this image. This is a real prototype at Berkeley of very similar concept as compared to ours. It's basically fiber which is moved in 2 axes, radial and angle, so you have polar coordinates, and you patrol a small field of view which is about 40 arcseconds. So each actuator will be able to target one object. So you can basically have a software that will be able to configure the field and point and do the acquisition of all the targets. And in the center, you will have this super Ifu that will be able to do 30 arcseconds by 30 arcseconds 3D spectroscopy. So this is some details. You can see better here. So you have translation motion and rotation motion. So you have, in this concept, the Berkeley concept, you have 2 motors. In our concept now, I don't remember if we have 1 or 2, who's to mind now? 2, also 2, but the movement is done in a different way, but at the end is the same. So we have this agreement with a company in North Spain. So we also got a grant from the SEDETI, about 300,000 euros. They got the grant because they are the company for the construction of the robot prototype. So we are going to build the robot for 19 actuators. We will do just the central part, and we have the money for that. We believe that by the end of this year, we will have our own prototype of one actuator. Moving to the optics, we spend a lot of time, more than 1 year, dealing with the problem whether we can use a single fiber of 1.5 arcsecond or not. Because if you have a single fiber of 1.5 arcsecond, then if you work out the optics formula, you end up with a very big spectrograph. You end up with a beam size of more than 400 millimeters, and that will be really impossible to build. So it's basically approaching to huge instruments like Deimos or something like that. So this is the basic formula. And so the solution that we approach, and we had very good inputs also from different people. I think at the IEC, Jose Luis Rasilla and others, and our consultant in Santa Cruz, California, Harlan Epps, also helped us to suggest that the only way would be to do some kind of imaging slicing, if you want to call it. But at the end, is basically that each unit, instead of a single fiber of 1.5 arcsecond, will be 7 fibers of 0.5 arcseconds. So you will end up with this hexagonal configuration. Here is these 7 micro lenses, and they are glued to 7 fibers. The reason to have micro lenses is because we need to change the focal ratio of HGTC F17 to F5, which is the ideal focal ratio for the spectrograph. And so each group of 7 fibers, which goes into each actuator, remember the previous diagram. So in each actuator, this cable will be a group of 7 fibers. So each 7 fiber will go to the slit, and each fiber will be attached to the other in groups of 7. So the light of an object will be collected by 7 fibers. So the spectra extraction will be the sum up, maybe signal to noise weighted of these 7 fibers. So this is a drawing of the buttons down here at the IEC by Felix Gracia, yes, where you have the micro lenses. Well, it should be 7 in this case, but he put more, doesn't matter. And then you have this aluminum support and all the fiber, the jacket, and so we really need now to build up a prototype of this button, maybe not having the micro lenses, but we really need to build up the group of 7, the cable group of 7, to help the mechanical designer of the actuator to test the flexures of fibers and to close our design. So this is the fiber optic transmission. This is broadband optical fibers. And if you look at it, it's difficult to see from there. But if you start at 4,000 angstroms, which is here, for 10 meters of fiber, you have 80% transmission. And if you go to 5,000, then you have more than 90% transmission, except here is atmospheric window. This is due to the OH depletion in the fibers. So you go all up to 1.7 microns with very high transmission. So fibers now do have very large transmission as compared to slits. Of course, with fibers you lose some light due to the fact that you have the micro lenses, the polishing, and at the end you might end up with some light losses of 10%, 15%, depends how good you are on the manufacturing, but ideally the fiber will respond with this curve. If you go to the very blue, then you have a problem, but this is not our case. Yes, but I can show you for 40 meters, and beyond 5,000 angstroms, it doesn't really change much. The problem is below 5,000 angstroms for very long fibers. Transmission go even down to 50%. But for beyond 5,000, for 40 meters, transmission might go from 95% to 90%, something like that. So this is our dual visible near-infrared design for the spectrograph. Remember, we have 10 identical spectrographs. And it's exactly, if you look at this layout, it's exactly the same that you will see for the slow spectrograph. Okay? So we believe that this is a very nice solution for us. It's simple, and there's no any technology challenges here. So the challenge is to build it, right? That's and to be sure that it's efficient and its quality is good. So here is the slit. That's the slit. It's about 110 millimeters or so. So fibers goes to the slit, and the light goes to a collimator, a mirror collimator, which is F5. Then light goes back to a dichroic that split the light into a visible channel and the near-infrared channel. The light is split at 9,500 angstroms and goes to the visible arm. There is and the near-infrared. Visible goes from 4,000 to 9,500, and infrared goes from 9,500 to 1.4 microns. And this is the different resolutions that we are thinking for both arms and the different spectral coverage. So let me answer Cassiana's question first, and then I will highlight the main features of the instrument. So the question I think you have is why to start at 4,000 and maybe not 3,000, or the resolution. Okay, sorry. I thought it was the wavelength. No, you mean in this design, what limits the maximum resolution? Yes. What limits the maximum resolution is to keep the cameras fixed. So if you allow articulate the camera, you can accommodate high resolution modes up to a limit. I don't remember now, but for example, let me put it in other words. When we thought about this spectrograph, we wanted something very, very stable, something that is sitting in an optical bench, and with very few moving parts. Here is only the cameras are moving for focusing, and then you move the grisons to select the different grisons, and that's all. Okay? And with this configuration, which is fixed for the cameras, okay, the maximum resolution that you can accommodate in the visible arm at the calcium triplet, for example, 8,500, will be 6,000, for example, with spectral coverage of 1,000. You can even go higher, maybe 7,500, but with a smaller range. But you cannot go to 20,000 unless we believe, because we did that study, but I cannot guarantee that it will work, unless you allow to rotate this camera. If you allow to rotate this to a given angle, you might allow to have resolution 15,000 with VPH. I mean, that will be only 500 angstroms coverage. And then if you want to cover the whole spectral range, you need like 20 grisons. That's why this design is not optimum for higher resolution. It will be possible to accommodate some options, some upgrades, but in our original idea, the feasibility study, to satisfy this requirement of resolution 20,000, we proposed to build a separate spectrograph, which is in the document, that will be focused only to resolution from 10,000 to 30,000. Because it's different concept. Combining, we spent 2 years with that problem. Combining both requirements is very, very hard. It's possible, but it's very hard. But we believe that, and we have done the optical design, that in the visible arm, we can go up to resolution 6,000 with 1,000 spectral coverage at the near infrared 8,000 angstroms. And this is very important because I was motivated to study this just this summer. I met a guy from Caltech, Josh Simon, who's studying determining radial velocities of stars, of these very small satellites in the Milky Way. He's using Deimos with resolution 6,000, and he's able to get a velocity accuracy of 2 kilometers per second. He has the papers, he has demonstrated that with the appropriate signal to noise, resolution 6,000 at the calcium triplet, you can get 2 kilometers per second accuracy. So we are able to do that. And so the major features here are that we have a low resolution mode, 1500, that gives you a very large spectral width. For example, you can have about 4,000 angstroms coverage with 1500 resolution, and you can have with about 4,000 angstroms in the near infrared, 3,000 resolution 3,500, you can have 2,000 angstrom spectral coverage. So the main motivation of this design was try to get the maximum, the largest possible wavelength coverage, and a resolution which is a good compromise to be able to go deep and resolve the OH lines. And this resolution is okay, so maybe higher would be better, but it's a good compromise. And in the near infrared is the same. So we have, with the low resolution, a huge spectral coverage, and with high resolution, we have, for example, resolution 4,000 in 1.2 microns. We have almost 3,000 spectral coverage. So which is important about this design and unique is in a single exposure, because we have this dichroic. If you pick up resolution 1500, you will be able to go from 5,000 to 1.4 micron in a single exposure. And in high resolution, it depends where you are, you can also do simultaneous optical and infrared, and do, for example, if you want to do redshift 1 survey, you can go from resolution from 7,000 angstrom to 1.2 micron almost in a single exposure at resolution 4,000. Detectors. So we want to use these CCDs, which is the Berkeley Lab CCDs. So we have a collaboration with Berkeley. They are willing to give us an engineering array and also they are willing to discuss a possible contract for getting one science grade array. So this is unique detectors that allow you to get a quantum efficiency of 80 or 90% at 9,000 angstroms. So this is a factor of 2 win in sensitivity in quantum efficiency as compared to optically thin detectors. These are optically thick detectors, so they don't have fringing. Okay, and that's, everyone knows that fringing is a killer for deep spectroscopy. So we have here a unique spectrograph that will have no fringing and very high throughput in the very near infrared. So if you do calculations, maybe it's too optimistic, but you can end up winning almost 1 magnitude in spectroscopy by having no fringing and a factor of 2 in the quantum efficiency for the same spectrograph design. So this is a very unique feature of this system. In the near infrared, you have the classical Rockwells. So the location, focal station needed. So we need to know where to put the spectrograph. We know which telescope we want to put it, but not the station. Competitors, as I told you, for the multi-object, we have this Subaru WFMOS, which at the moment is pending. No, nothing is happening. And we have Muse for the SIFU, but Muse is a special instrument, and the SIFU, in our case, is a plus. It's not really the main driver, but for free, you have the SIFU, and the SIFU for free is already a huge contribution, because you will end up with 30 seconds by 30 seconds in the optical and near infrared, and that's something already unique. I will not go in tables, show comparison with everything. So I will end up the presentation with some, which I believe, important thoughts about the role that site can play in the future. The kind of technology, the kind of approach that we are proposing fits very well into future instrumentation of the extremely large telescopes. So we were invited to participate in a proposal for this call, which is Advanced Study of New Instrument Concepts for ELT. The price, I guess, is to go for dinner and no more, because with 1,000 euro, I don't think you can do much. But so the recommendation of the science working group, of the ELT science working group, was to emphasize a very strong science case in an instrument which provides multi-object spectroscopy from R band to H band with multiplexity up to 100, with a field of view of the order of 10 arcseconds, and with spectral resolution about 3,000, and also include resolution 5,000, 10,000. If you look at this, it's exactly our instrument. So that's it's good for us. We feel good because we see that we are moving into the future. So the contribution of SIDE to the big science, this is also important because it's a good seller, so you need to tell agencies that you will make a huge contribution to the science development. There is a nice document produced by ISO working group. They did 3 reports on different subjects. One of them was on fundamental cosmology, and they end up with recommendations which basically point out into the need of the construction of an instrument like this. So I will not go into the details. They give a lot of reasons, but they basically say that, for example, science calibration photosees, more than 100,000 redshifts. They talk about 1 million redshifts. So they give all sorts of justifications and the scientific reasons for an instrument like that. That will be really important for cosmology in that case. Okay, this is one of my last slides. So the challenge is to choose the right strategy to guarantee that site at GTC will lead the survey spectroscopy in the next decade. And a few words about the new site consortium is that we want to form a new consortium to focus on the construction of this multi-object spectroscopy science project to attend the recommendation of GTC of a new call for key projects. And finally, within this context, we are building this mini site, which is a pathfinder, that will be soon proposed as a visitor instrument to GTC SAC, and we hope to see first light by end of 2010. It's very ambitious, but we are in a very good way. We are doing review, we are doing PDR of important parts of the project. Hopefully by next April, we will do PDR of the whole project. Now we are doing PDR of the optics, of the robot. And mini site is, remember, this is the dual spectrograph. It's just one dual spectrograph of site, but we will build only the visible arm. So it will be only the visible arm, and in terms of the focal plane, this is how it looks like our focal plane. We will have 19 actuators, and in the middle we will have a little eye view. So altogether will give us a multi-object spectroscopy in a field of view of 3 arc-minute diameters of 19 objects, and in the center we will have an eye view of about 10 by 10 arc seconds. So this is a very important initiative because it will allow us to probe the concept. It will allow us to show that fiber spectroscopy could be really efficient and important, and also it will allow us to do science. And we have already very nice science cases. We have been making a lot of effort to find niche, science niche, where we believe we can be really competitive to go to the TAC, or to the CAT in this case, to fight for telescope time for this instrument. And I will be very happy to talk to you, to discuss any ideas, welcome any suggestions, and if you want to help, we are very much open. So thank you.
Okay, so we have about 15 minutes for questions.
The new?
The money.
The budget? Do you mean for the whole, for this mini site, which can give you an idea of the cost of the spectrograph, no? So I didn't calculate the budget of the new site because I had no really time for that. But if you have this project, which is mini site, which is already a very important part of site, because in 2 years and a half from now, we will have developed most of the components of site at the end, right? So the whole mini site project, being realistic, including manpower, is about 1.5 million euros. This mini site. We have spent already 1 million in the feasibility study.